going to be a quick video about TomoPlus. We're actually going to go through a project and build a 3D project. So just to start off, I have a SIG-Y file that's got the geometry and the headers, and that's the only thing I have in that directory. So I'm just going to go start a new project, give this project any name I want, call 3D, browse and select the SIG-Y file. I can check to see if the headers are in the locations that I'm expecting them to. So here I see the trace headers from bytes 1 to 240. I can display that in several different ways. What we call standard has some information stored or shown in 4 bytes, and this has it displayed in 2-byte integers, etc. So you can display that several different ways. You can check to see if you have the information that you need for to describe the geometry in the locations that are specified in this map file. If you need to change anything, you can simply change the byte location here. If you have first breaks already in the data, you could, in bytes 221 for example, you could also import those when you build the project. In my case, the SIG-Y already has the information in the headers in the same location as what we call our standard SIG-Y. So I'll just assume standard SIG-Y and hit apply. It checks the first few shots to make sure that there are no obvious problems, and then I say continue, and we're actually building the project index now. It requires that there are unique shot and receiver IDs. So that's one of the checks that this will go through, just to make sure there are no duplicate shot IDs or duplicate receiver IDs. So while we're building the project index, I'll just point out that there are some utilities on the main software launcher that may be useful, and there are also some utilities on the smaller TomoPlus launcher that may be useful. One such utility may be the convert file format. If you have existing first break picks in a GLI format, for example, you could convert those picks to a GTT file, which is our GeoTomo format, and you could actually build a project with that GTT file instead of using the SIG-Y. So that's another option. Pardon me. Now we see that the project has been built. We see our shot receiver map. Shots are in red, receivers are in yellow. I'll close that for now. And we see we have a summary of information, total number of shots, the coordinates, shot intervals, etc. We don't see any blue or red warnings here. The important thing here is shot ID unique, receiver ID unique. If there are any problems with non-uniqueness, these would show up in red. Sometimes you may get a blue warning message, and that may be the case if you have several shots in the same location, but they all have different IDs. That would be fine. So I'll close that. If I did have problems, one thing I may want to check is under information, shot unique information. That will go through a series of checks just to be able to identify any problematic shots or receivers. Same thing I could do with receivers. Check for any non-uniqueness there. So it's a good idea to run those 2 checks after you build the project. Here you can obviously jump to any shot you want. You could go one at a time, or you could skip through every 100th shot if you wanted. Some simple tools here to change the way the data is displayed. But typically what we'll do here is we will, since we're going to do this quickly, we'll apply some type of linear move out. I clicked on the D over V, and I could move the mouse into this window here to get some velocity. Maybe I'll try something like 4100 and apply a shift of 300 milliseconds and apply that. So all I'm doing here is applying a linear move out to the display here, and I could use any of these tools to try and pick first breaks. One manual picking tool would be Tracker, where I can simply make 2 mouse clicks and it will fill in spaces between them. But typically what we'll want to do is run a batch job. So I'll run one of these auto pickers. FB Vibe and FB Dyn are the pickers that we use most often. So they have similar interfaces. What we're going to run right now is FB Dyn. I'm going to tell the program the first arrival is actually a trough, negative. I'll pick all the shots here. I'll typically, the minimum tracking step, 20 milliseconds from one trace to the next one. Since we've got LMO applied, that will be a reasonable choice. I can select the machines I want to run this job on, move a machine over from the left to the right, choose any machines that I want to run this job on. In my case, I'm going to run 20 cores per node, and I'll apply. And now this is going to go ahead and pick first breaks on all of the shots. This FBDyne is an algorithm that's more geared towards energy ratio above and below a sample on each given trace. When I started that job, I did get a log window pop up here, and we can see now that that's finished, but I will get a completion message here in a second. Just to mention, the FB Vibe is a picker that's in its algorithm is more geared towards coherency from one trace to the next. So two different algorithms you could use. There's a third one here, automatic tracker with seed picks. That would require you'd need at least 2 picks on every shot, and you could run that, and it would fill in the picks on any traces between the existing picks on those shots. I'm wondering whether this completion message came up in the back. Apparently not. Oh, there it is. Okay. So that just told me I picked all of the shots. Now I can see if I bring up the shot receiver map. If you remember before, the shots were red, so any shots that now have a pick, at least one pick on them, or at least one trace that has a first break pick on it, they're now shown in green. There are some QCs here. Pick similarity will check the picks on any given shot to its neighbors and come up with an average difference. Basically, any high values for pick similarity means that the picks are very different on those shots. There are values here from 7 to 49, so I want to highlight these problematic shots. So if these have very high values, then they are not very similar to their neighbors. So I can go up into this box, specify a threshold, let's say 30 milliseconds, hit return, and it's grayed out all of the shots that are not problematic and left the, in this case, the 4 shots that have a high dissimilarity, basically. So I can click the arrow here, and it will just jump to the first of those 4, and I can take a look at that shot and decide whether I need to modify these picks, whether there's some other problem, perhaps a geometry problem. In this case, I could try and update some of the picks, for example, by using tracker. Basically, I can step through those 4 problematic shots and identify any problematic picks or any potential geometry errors. There's also reciprocal error, which you could also use. It's more efficient in 2D, where you actually have coincident shot and receivers, or closer to coincident shot and receivers. And once you've run the travel time tomography, you could also run the shot misfit as a good QC. There are some other QC tools here that you can use, pick density display, etc. So there are other QCs here in the map that you can take a look at. Once we've gone through and let's say we've edited some picks here based on our QCs, we would then go ahead and export those picks. So we're going to export a travel time file, which contains the geometry basically and the first break picks. So we've exported that. Now we're ready to go forward to the next module. The first module turned green. Now we're going to go to 3D time, where it's automatically imported the highest number GTT file that we just created. Basically, the first step I'm going to do here, if I could look around at some of the individual shots. We have the travel time for one individual shot. We have our shot receiver map. The first thing I'm going to do here is these are the picks for all of the shots in the entire 3D. And this will remove poor picks. I can actually draw a polygon, any polygon around these picks that I would consider anomalous. I can draw several polygons, and basically I can remove any outliers this way. And these polygons can intersect if we want. So I'll just draw a couple there. I'll click this Save Diskette. And there I've created a new GTT file now that basically has gotten rid of a lot of the outliers. You don't want to be too aggressive with this in areas where you have a lot of topography or a lot of near surface variation. You don't want to be too aggressive with that. You could also divide this up into subsets and remove poor picks on subsets. In this case, we've removed some outliers. The next thing we'll do here is a rotation. We want to rotate this data set so that it fits into a rectangle with less white space, essentially. We don't want to build a velocity model that has a bunch of cells that won't get updated, so we're going to apply some rotation here. So this will fit into a smaller rectangle. So I've just opened that, and now I can mouse drag and hold along one of the receiver lines. It's filled in the azimuth and the origin, and it's going to output a new GTT file. And I'll click Apply, Close. And now I've got the GTT file. It's now been transformed to local coordinates. The next thing I'm going to do is build an initial model. So this third icon here, the same, again, this is the pick density display for all of the entire 3D. So I'm going to build an initial model, my starting velocity model. So my first mouse click can be somewhere other than 0. So this is the end of the first refractor, let's say, end of the second refractor, end of the third refractor. And right mouse click brings up this window, and basically I'm going to default this. I can change the cell size if I want. In this case, I'm using a cell size of 68 by 68 by 34 meters, and that's the receiver interval by receiver interval by half the receiver interval. This receiver interval was estimated in the first stage when I exported the GTT file. So I will build this grid model, and now I'm ready to run tomography. So I'm going to go ahead to 3D imaging because I've got an initial model built and I have my travel time file. And here I'm ready to run travel time tomography. So here's the initial model filled in for me by default. Here's the travel time file. In this case, I'm going to change the smoothing control to be 10, and I'm going to leave I'll change these grid factors 2 to 1. And just in order to run this quickly, we'll, again, we can select some nodes. I'll use the same ones as I did previously, and I'll start running this job. So this will start running several iterations of travel time tomography, where we're going to be updating the velocity model at each iteration, trying to improve the misfit between the true first picks that we picked and the synthetic picks that are generated from the resulting velocity model. So this will take a little while to run. At the start here, while it's running, I'll just point out that there are some advanced parameters here. You could limit the velocities that you want to allow the model to be modified. You could also change the offset range if you want, and there are some other advanced parameters as well. For now, I'll just point out, okay, this is at the start of the iterations. I'll just point out right now, you can actually go ahead to 3D View M, where you're going to be viewing the model. And this is actually the starting model that we built, just from all of the picks. Just take a quick look at the starting model. You can slice through. There is a fair amount of topography in this data set. And we can see that here the gray represents the air velocity. And we have a 3-layer velocity model as our starting model. For now, we'll just go back to this interface here, and we'll see that's in the second iteration. I'm going to stop this recording, and once this is finished, I will start the recording again. Video, and we can see that this job is completed. It took 10 minutes to run. We can see that the misfit has gradually gone down with each iteration. This is the overall RMS misfit of all of the shots. And this display down here, I can see if I click on this triangle here, that will make this display fill the entire page. And these are all the shots and their associated misfits. So we can see that there are some values, some shots that have a high misfit. We can look at this on a receiver basis as well and see if there are any areas that have high receiver misfit. I'll click this triangle, go back to this display. One thing we'll want to do after we run the tomography is take a look at the actual synthetic. So we'll overlay the travel time, and we will load in a GTT file that has the same name as the velocity model we created, _syn.gtt. And we can see in blue, that's our synthetic travel time file that's generated from our final velocity model. So we can see in some areas, even though we had poor pics, the synthetic travel time fits the data fairly well. We can see other areas that the synthetic travel time does not fit very well, and that would lead to an overall higher average shot misfit. So we can see in a gross sense these look okay. One thing we can also do is load up the shot receiver map, take a look at the shot misfit, load in the rms.fit file, which is the same misfit that we saw in the earlier display in 3D imaging. And we can use the same criteria here where we would specify a threshold, say 20, and we see that there are 18 shots that have a misfit higher than 20 milliseconds, and we could skip forward to those and identify if they are poor pics or possible geometry errors. In our case, we did one thing I didn't highlight really, that I used a grid factor of 2, 2, and 1 in X, Y, and Z. So the original cell size was 68 by 68 by 34 meters. So the ray tracing will be done using that original cell size, and the velocity updates will be done using 2 times 68 and 2 times 68 in X and Y. So it'll be a larger effective cell for the velocity updates. I did that in this case just to save a bit of time. Also, in some cases, it can make sense to use larger effective cells for the first few iterations to get the overall global solution, and then use smaller inversion grid factors. Once you've run several iterations, you can then take the output, use it as the input for another run, and run a few more iterations to create a new output file. In our case, we're going to take a look now at the velocity model, and I can open that velocity model just to take a look at it. We can slice through it in different X, Y, or Z. We'll notice that this has a slightly blocky look, perhaps. One thing we can do is on the X or Y, we'll see the actual slices, and we can see the actual vertical slices that way. So the model in general looks a little blocky, but that would improve if we used the smaller grid factors. Another thing we want to take a look at is we would also want to take a look at the ray density, and this tells us where we've actually ray traced through the model. And so now we're looking at a Y slice, and we can see wherever there's blue and yellow that we've actually ray traced through this part of the model. And we take a look at a few other places. What we want to hopefully avoid is that we have big holes in this ray density. So we can take a look at this in different dimensions as well. We can slice through it vertically, and we can see from the top. We get an idea of where we're actually ray tracing through. So sometimes you may see a bit of a geometry footprint on 3Ds, but what you hope to do is try and minimize that footprint by using a cell size that's large enough and a grid factor that's large enough, and perhaps the smoothing control as well. One thing you want to try to avoid also is your rays going through the bottom of your model. In my case here, it looks like some of these rays are actually going through the bottom of the model, and I may want to increase the depth of my model before running more iterations. So in our case, I'm going to say that this is a reasonable model just to demonstrate how we're going to proceed forward. I'm going to need to, if I'm comfortable with my solution, I've checked my QCs, I'm going to now want to go ahead and pick a floating datum and an intermediate datum, and then we're going to use those to calculate statics. Typically what we do to calculate a floating, or to generate a floating datum, is we use the topography. And so I'm just moving the Z slice down. I'm going to go File, Import Layer at Treetop. So when we generate the models, there's also a Treetop file generated with the same name as the velocity model. And this is the topography. And now I see I have a problem with this display, so I'm going to stop recording for a second and change to a different box that will allow me to display that property. What I've done here is I've restarted the software, launching it from a different server that will allow us to display the 3D property. So again, I did File, Import, Layer, Treetop, and that displays this layer, which is the actual topography. And I will use a smooth version of this as my floating datum. So I'm going to right-click here to highlight the edge of that. So I've activated that layer. I'm going to go over to Edit Smooth Setting and change my smooth settings to be slightly lower. And click Apply. So that's just setting the smoothers. And now, since I've activated this layer, I can go up to this icon here and smooth that layer. So I'm going to call this my floating datum. And now I have a few options for generating an intermediate datum. And what I'm going to do here is take a look at the slice, the Y slice, and maybe get an idea of what velocity I might want to use to extract an isovelocity interface. You can pick an interface manually on each of these Y slices if you like, or you could actually copy this and or load in the topography and shift it down and create a constant thickness weathering layer. In my case, I'm going to try to extract an isovelocity interface. And I'm going to say, show me an interface that's generated perhaps at 4,100 meters per second. There's the interface there. I'm also going to want to apply some smoothing to that. So I'll right-click to activate this layer, and then also go up and smooth that layer. I can smooth that a couple times if I want. And now I can go into the slice mode again, just to check to make sure that my layers aren't crisscrossing. And I can go through and see if I like that layer or not, or if I want to choose something slightly slower so that perhaps it's not quite as deep. In this case, I'm going to assume that this is okay. Once I'm satisfied with my layers, I'm going to go File, Save 3D Datum. And so that's saving both the floating and the intermediate datum. And now I'm ready to go forward and calculate statics. I'm going to go forward into the 3D stats module, statics calculation. I have my velocity model, the datums that has the floating and intermediate datum. This GTT file has all of the shots and receivers in it, and this GTT has my best first break picks in it. I'm going to put in a final flat datum. My replacement velocity, I'm going to use 4,100 in this case. Minimum refraction offset. The last 7 boxes here are all going to be used in calculating the refraction residuals. So we're going to calculate a long wavelength static here, as well as refraction-based residuals. So I'm going to, I believe I have the best picks in the range from 500 to 3,000 meters of offset. And I'm going to let the rest of these default and hit Apply. And then we'll explain each of the statics components that get generated. So it's going to use the velocity model, the datums, and the geometry to calculate a long wavelength static to move from the true shot receiver locations down to the intermediate datum, and then using the modeled velocities, and then back up to the floating datum using the replacement velocity. So that's the long wavelength static to floating datum, and that's what's displayed here. Then it takes the, it's going to calculate a refraction-based residuals, which is shown here, and that's done by applying the long wavelength static then applying a reduction velocity, or essentially a linear move-out velocity that is calculated internally, and then taking that travel time, smoothing it, and the difference between smoothed and unsmoothed is decomposed into shot and receiver residual statics. That's what's displayed here. The next static item is the sum of the first two, and that's the total static to floating datum. And then there'll also be a total static that will move from the floating datum to the final datum, and that's displayed here. There are a few other components: elevation, shot depth, and the intermediate and floating datum values you can take a look at as well. But these are the statics that you've generated. You could, at this point, this is an ASCII file, so you could actually use that ASCII file. You also have the option of exporting these statics to a file. You can export any component of these statics. Typically, people would use the total. I think a lot of people will use total statics to final datum, and just create some file. Just create some file that will have the shot and receiver statics in it, or you could output just the shot statics first of all, and then the receiver statics, and you can output any one of these components in addition to the total static. We won't do that in this case. One other thing we'll want to point out here is you've got your statics, and now you can actually take a look at your data with and without those statics applied. So let me make this a little bit bigger. And we're in the processing, which is the same as the 3D prep module. We're going to click PS to create a processing sequence. In this case, we'll just do AGC and then statics. And we'll grab the statics file we just generated. And in this case, we'll apply a total static to floating datum. So I've determined the flow. In this case, I'm not going to run a batch job. I'm just saying apply here to save that flow. We can see the sequence here, and now I'm able to step forward using these arrows. And it's applying the AGC now, and then I'll be able to step forward and see the application of the statics. So I'm using the arrow key on the keyboard now. Before statics, after statics, before, after, before, after. We could go ahead to any shot we want and see the application of the statics there. Before, after, before, after, before, after. So that's where a lot of people stop. They've QC'd their statics on a shot basis, and if they're comfortable with them, they'll export them. And